Hello, are you exploring possible solutions for the statistical modeling of NS1 time series and or interested in learning more about the concepts of random intercepts and random slopes? My name is Jimmy Lapping. I'm a psychologist and statistician with an interest in a wide range of research topics including physical and mental health. And in the next few minutes I explain through a real-life example with data collected via the Samsung Health app how, for some types of seasonal and cyclical signal subject time series data, models including random intercepts and or slopes can be useful to make sense of the data. If you haven't heard of the Samsung Health app yet or want to learn more about it, in one of my previous videos on this channel I provide an example using daily sleep and walking data, and in this video I zoom in on the walk data that I introduced in that previous video. The Samsung Health app allows users to download one's own data in the form of a comma-separated value or CSV file, and the analysis that I discuss in this video can be done in open source software such as Jamovi and R. So what we see here are two graphs of the same random intercepts and slopes model of 52 weeks of daily distance in kilometers walking data, 364 consecutive days, that I introduced in the video that I mentioned previously. In each of the two graphs, we distinguish between weekdays, that is Mondays to Fridays, on the left, and weekend days, hence Saturdays and Sundays, on the right. The graph on the left presents the actually observed walking data, whereas the graph on the right presents only the outcomes predicted by the model for each of the 52 weeks. As we can see, there is considerable variation in intercept, that is predicted walking distance on weekdays, and also in slope, or the difference in predicted walking distance between week and weekend days. In weeks of relatively little movement, we tend to see little movement during both week and weekend days, and perhaps even less during weekends. Whereas in weeks of more movements we tend to see more positive slopes indicating more kilometers during weekends. The way we treat the data here is that both the weekly walking distance and the difference between week and weekend days are at least to some extent a function of random movement. We are not interested in making forecasts for any time points after the period measured, but simply in making sense of the data observed in this 1 year time window, which can be broken down into 52 weeks of 5 weekdays and 2 weekend days each. And we are trying to understand this short-term seasonal or cyclical component using random intercepts and slopes. In the graph on the left, the thick line, which goes nearly horizontally, indicates that in this time period, on average, there is hardly any difference between week and weekend days. But the other lines indicate that there is considerable difference between weeks. If we focus on the thick, nearly horizontal line, we explain only about 0.1% of the variation of daily walking distance, whereas with the inclusion of the random intercepts and random slopes component, we explain about 29% of the variation of daily walking distance, because both random components help to account for the variation within and between weeks to a considerable extent. And yet, contrary to models which treat weeks as fixed effects, this model, which treats weeks as effects as random, requires only 1 degree of freedom for the random intercepts variance, 1 degree of freedom for the random slopes variance, and 1 degree of freedom for the covariance of these two variance sources. If we were to treat week as fixed effect, we would need many more degrees of freedom for all this. And this is what the model looks like visually when we plot the observed data here in blue against the model in red over the 52-week time period. We see that there are weeks during which the daily walking distance is around 5 kilometers or less, but there are also weeks of on average 7 kilometers daily walking or more. But does this model adequately account for the features of the time series data? Well, to answer this question, we can have a look at the residuals. So here we see different distributions of residuals. On the left we see a distribution of residuals at week level. Next, the three histograms in blue provided distributions of residuals as well as those of random intercepts and slopes across the 1 year time window. Although these distributions are not nicely bell-shaped or normally distributed, we do not see concerning levels of skewness or extreme observations either. And finally, in the graph in the middle with lags and the autocorrelation values below the graph, express the degree of autocorrelation of residuals at different lags. One can run formal tests such as the box test, which in this case do not indicate any serious concerns regarding significant degrees of autocorrelation. Significant degrees of autocorrelation, for example plus or minus 0.2, would indicate that this model does not appropriately account for the serial correlation in the data, but in this case there is little concern. And finally, we can assess the distribution of residuals over time, which in this case centers nicely around 0, with not that much difference in dispersion over time. Formal tests of heteroscedasticity do not indicate any significant heterogeneity in the dispersion over time. To conclude, although like other models, the random intercepts and slopes model is by no means a perfect model, and we cannot use it to make forecasts beyond the period studied, it does provide a possible way to make sense of the data, explaining about 29% of the variation with relatively few degrees of freedom. Okay, that's it for this video. I hope you find this useful, and if you have any ideas or suggestions for future videos, feel free to leave a comment below this video or contact me via the email address shared in the description below this video. Happy New Year, all the best, and thank you for listening, and see you soon.